Fundamental chemistry in the contemporary society. Welcome to this resource of Karazin University, one of the oldest classical universities in Eastern Europe. Chemistry has been teaching within its walls from the very first day, for more than 200 years. Authentic universities teach, first of all, fundamental disciplines. Accordingly, the School of Chemistry opens the door to the realm of fundamental chemistry. Chemistry, in simple words, deals with various situations when one substances convert into some other substances. The vast majority of people has more or less clear understanding about chemistry from the ordinary school. But what does the attribute fundamental mean? It is not so simple to explain this popularly and briefly, but still some understanding is required prior to discuss the role of fundamental chemistry in the contemporary society. I think that the ranges of spatial and temporal scales provide a proper insight. Today, chemists can operate with a single molecule, and even with a single atom. This slide shows three popular illustrations of the capabilities of scanning tunneling microscopy. The logo of the IBM Corporation is made from xenon atoms arranged on nickel surface. The so-called carbon monoxide man is constructed from CO molecules on platinum surface. Iron atoms positioned in a special way on copper surface produce quantum corals. Chemists are interested, first of all, in examining separate molecules adsorbed on various surfaces and in manipulating with such molecules. Two following examples illustrate this. One possibility is to take a carefully prepared metal surface, to place an examined molecule on it, to situate the tip of the scanning tunneling microscope above this molecule at an appropriate height, and to arrange the electric chain between the tip and the surface. If everything is properly adjusted, two potential barriers for electron will appear, one on the tip and the second on the molecule. The space between them is a resonator, actually nanoresonator. An electron trapped in this resonator can pass through the molecule to the surface only when in resonance with one of molecular vibrational transitions. As a result, the dependence of the tunneling current on the applied voltage will give the information about the vibrational spectrum of a molecule. This will help in particular to understand how these adsorbed molecules will react with a different adsorbed molecule. One more possibility is to selectively broken a chemical bond. It is also possible to bring two molecules together in a proper orientation and to make them react with the formation of new molecules. The next slide illustrates this. The first step is to place two molecules of iodobenzene in the proper orientation and at a considerable distance from each other. Then the iodine atoms are selectively detached. And subsequently moved away. Then two phenyl radicals are brought close enough to form the covalent bond. And finally, two iodine atoms are brought close enough to form the iodine molecule. The so-called Nano Mobile is one more example. What you see now is a single molecule with this quite complicated chemical formula. It demonstrates virtuosic capabilities of modern chemical synthesis. When placed on a gold surface, it behaves as a small car, and it is proved that fullerenes that play the role of wheels actually rotate when the molecule is pushed by the tip of scanning microscope. Nano Mobile is only one of numerous illustrations of the actively developing field of nanochemistry. These three examples represent the lower limit of the length scale and a very interesting boundary with the fundamental physics. The opposite boundary of the range is the world of very large molecules, polymers and supramolecular structures capable of self-organization. This includes, in particular, molecules that govern our life, DNA, enzymes, and so on. A relatively new achievement is the possibility to experimentally observe the dynamics of such big molecules with the help of super-resolution fluorescence microscopy. This slide illustrates the behavior of the allosteric center of an enzyme. And the next slide is an example of the direct visualization of the DNA molecules. These two examples illustrate in particular very interesting boundary with the fundamental biology and medicine. Now turn to the time scale. A natural unit of time for human beings is 1 second. This is approximately 1 heartbeat. This is tangible. The lowest limit of the time scale is attosecond. The prefix atto means 10 to the power of minus 18. 1 attosecond relates to 1 second as 1 second relates to the age of the universe, which is estimated to be about 10 to the power of 17 seconds. The attosecond time scale is tempting to chemists due to the prospect to get a deeper insight into the behavior of electrons in atoms and molecules. For example, to make tomograms of atomic and molecular orbitals. In a hydrogen atom, the electron makes one turn around the nucleus in about 150 seconds. For the present, the attosecond level is many ambitious plans and relatively few results. But the next step, the femtosecond level, is rich of striking results. The prefix femto means 10 to the power of minus 15. This time scale is essentially important for chemists due to the possibility to get an insight into the elementary event or elementary act of a chemical transformation. We will explain this concept later, and I will explain it. Imagine tourists who go through the mountains. They know that a warm sea is waiting for them at the end of their trip. But to reach the sea level, they need to overcome a certain height, and they will look for a minimal possible height, the so-called mountain pass or neck. The schematic representation on the right is often termed the saddle. Point X is termed the saddle point, and line CXD shows the optimal route. This, well-known for many people situations, is generally a good model to explain some details of an elementary chemical transformation. When two molecules react, this also may be represented as a travel through a mountain-like landscape, with two essential peculiarities. If we talk about the tourist route, two tourists at the starting point and at the finish point are exactly the same tourists. On the contrary, if we talk about reaction coordinate, two molecules at the starting point and at the finish point are different molecules. Reagents convert to products just near the saddle point. The second important peculiarity: people travel in three-dimensional space. The number of dimensions needed to simulate an elementary chemical transformation is considerably greater. It is impossible to draw such multidimensional landscape, and here I can only appeal to your imagination. But still, the factor chemistry is capable of making movies about elementary chemical transformations. And modern theoretical chemistry is capable to extract valuable information from these experiments. Two basic values are the rate constant and the activation energy. This is an example. Some subsequent snapshots illustrate the interaction of iodine and benzene molecules, resulting in the decomposition of the iodine molecule. Actually, about 400 femtoseconds required for the decomposition. All mentioned and many other similar results of fundamental chemistry excite one's mind, stimulate the imagination, inflame the intellectual passion, and at the same time there is a serious but. Research in fundamental chemistry requires highly educated and creative experts, many and many hours of their hard work, complicated and expensive equipment for experimental studies, supercomputers and appropriate software for theoretical analysis, also far from being cheap and simple. And all this inevitably raises the question whether all this demanded by the contemporary society. What are benefits to people who are far from science and are engaged in quite different areas of life? What can convince them that fundamental research is not just the waste of money? There is another side of the coin. What this majority of people think about science in general and about chemistry in particular. Let's ask the all-knowing Google. In response to the inquiry, does chemistry demanded in the contemporary society, this fantastically efficient search engine kindly suggests more than 6.5 million results. Answers for every taste can be found among them. from extremely negative to strongly invigorative. Chemophobia is an unavoidable part of our present-day life. Its adherents will not miss a chance to remind about numerous ecological problems like global warming, chemical weapon, genetically modified products, and many others. Positively adjusted people will appreciate that chemistry helps a lot in our everyday life. Medicines help to be healthy and keep high quality of life. Comfortable cars and cozy apartments require appropriate materials. Detergents are needed to maintain cleanliness. Many more examples can be given. Finally, some sympathizers will call chemistry the central science, Wikipedia among them, and will add that it plays the central role in the implementation of the sustainable development in the contemporary society. I have been teaching chemistry for years, and without a word, these sympathizers are the winners of my heart. Many experts are of the same opinion. There is even a book, Chemistry, the Central Science, that enjoys 12 editions. But what actually is behind this high opinion? The question is challenging. I think many experts will give an answer somewhat different from others. I will suggest my version. The ancient told that there are three things that one can admire endlessly. These are starry sky, sea waves, and fire. For me, the bonfire is a fascinating, romantic example of the spatio-temporal self-organization of a chemical burning reaction. It is worth noting that such spatio-temporal organization is one of modern trends in chemistry, and not only in chemistry. We will meet it again. Domestic gas burner is deprived of this fascination. Nevertheless, this is a related but much simpler example of the burning reaction of hydrocarbons, mainly methane. In this case, it is easy to write the chemical reaction. This reaction, which you see at the upper part of the slide, is apparently simple, but later we will see that it is simple only at a first glance. Many people use this reaction for heating houses and meal, but only few of them recognize two important things. First is that the burning of natural hydrocarbons is the most large-scale chemical process of the technosphere. It provides nowadays about 80% of the world energy consumption, which is estimated to be more than 500 billions of gigajoules, or 20 billions of tons of the oil equivalent. This includes industry, transport, space missions, agriculture, householding, everything. Second important thing, when we burn hydrocarbons in a simple manner, like in the kitchen, we waste 30 to 40% of the energy contained in the raw. Taking into account just mentioned scale of this process, this is enormous loss. The following explanation is required here. From the practical viewpoint, energy is subdivided into two constituents, exergy and anergy. Nobody in the world is capable of using all 100% of energy contained in the raw. Energy is the term for that part of the total energy which is inevitably lost. Exergy is the term for that part of the total energy that can be utilized. Nobody in the world can completely vanish the energy, but it is possible and absolutely essential to minimize it. It is instructive to follow several approaches of the fundamental chemistry to this global problem, and to illustrate in this way what does the central role actually means. One of these approaches essentially uses the concept of the chemical mechanism of a chemical reaction. What you see now is a partial list of elementary events participating in the reaction under consideration. The above-mentioned overall reaction, which you see in the upper line of the slide, is not the elementary event. Many and many saddle points need to be overcome by many and many intermediates on the multidimensional mountain-like landscape on the way from the two molecules on the left part of the equal thing to two molecules on the right. The complete list of elementary events counts 91 stages. Only 43 of them fit on a single slide. And this is far from the largest possible mechanisms. Thus, when the burning of the mixture of gaseous hydrocarbons is concerned, the corresponding mechanism counts about 3,000 stages and about 150 intermediates. There is an essential difference between the overall equation and any equation from the above mechanism, say equation 33. The latter represents the elementary event. We told above that this means the possibility to relate the corresponding energy profile to it, to estimate more or less accurately the activation energy, the kinetic constant, and its temperature dependence, and to use the action mass law in examining the kinetics. This is not a simple task, and this is the point where we need the spatial and temporal levels of a single elementary event. But it is much more complicated task to examine in detail the right reaction that represents the process as a whole. This requires to study all elementary steps that enter the kinetic mechanism, and to combine this information into a single whole, which is the system of nonlinear differential equations, quite difficult to analyze. It describes the phase trajectories in the multidimensional phase space. A three-dimensional projection is shown as an example. And it is a great art to find tractable projections that, like the one at the bottom of the slide. Considerable efforts and expenses are needed to such a study, but they are more than compensated by the understanding of the globally important process. And what is much more important, the possibility to control it. This may be done in several ways by the sought-out influence on one or another elementary stage, or group of elementary stages. One of possibilities includes three main steps. The first step is to increase the burning temperature as much as possible. Modern refractory materials admit temperatures about 1,500 of kelvins. The next step is to convert the mixture of methane and oxygen into the so-called syngas, which is a mixture of carbon monoxide and hydrogen. Note that this is a catalytic process which implies some changes in the kinetic mechanism. And the third step is to finally burn this syngas into another process, both catalytic and adiabatic. The result is impressive. The energy, the waste of energy, decreases from about 40 to about 15%. And now the key question is due to which this gain is achieved. The answer is as follows. Energy inevitably results from the irreversibility of a process. If one or another process includes chemical stages, then the chemical irreversibility is responsible for the main loss of energy. To significantly decrease this loss, the kinetic mechanism must be properly modified. And this is just the task of fundamental chemistry. That is how the global energetic problem and the concept of elementary event of a chemical transformation appear in one harness, in spite of very different spatial and temporal scales. The above practically twofold gain in energy is not the limit. We told earlier about the spatial-temporal organization of a process and the one of modern trends in science. In the context of the discussed problem, the idea is to organize the burning process as the so-called filtration combustion wave. Then there is no need in refractory materials. The temperature within such a wave may reach about 3,000 kelvins. And in addition, new nonlinear advantageous stage appear in the mechanism. This is one of promising ways of further decreasing the loss of energy. Even today, the complete reaction mechanism of hydrocarbon oxidation is updated and refined, and is widely used in examining various issues of burning process that still remain unresolved. Few words about another alternative, just to illustrate the variety of approaches to the problem. One of the essential ways to decrease the chemical irreversibility, and thus the energy, is the direct transformation of the chemical energy into electrical energy. This may be done in the so-called fuel cell. The general idea is as follows. Two electrodes are immersed in water and separated by a membrane. This membrane is permissible for protons, but not for electrons. Protons and electrons appear at the anode due to the reaction you see on the left. Protons move to the cathode directly through the membrane to react with oxygen, with the formation of water. Reaction on the right illustrates this. Electrons participating in this reaction have no other way than the external electric change, thus creating an electric current. The only product of this reaction is water. But how to put this general idea into practice? Both electrode reactions are catalytic by nature. One possibility is use enzymes as catalysts, say hydrogenase for the anode and lacase for the cathode. Enzymes are immensely efficient catalysts, but also immensely capricious. they will work only in the very friendly environment. This may be provided by nanoparticles of a wide gap semiconductor, such as titanium. Enzymes immobilized at these nanoparticles will not lose their catalytic activity. This is an example of modern bio-nanotechnologies. This approach has many prospects, but also many problems, like the poisoning of catalysts, insufficient power, heat utilizations, etc. I have addressed only one, but undoubtedly important social problem, energy problem, and try to illustrate the essential role of fundamental chemistry in its solution. It is possible to pull another thread from the tangle of social problems, medicines, materials, global ecology, whatever you want. And for sure, a keen insight will make explicit the significant role of the ideas and results of fundamental chemistry in responding to challenges of the contemporary society. By the way, in the whirlwind of our present-day life, we usually lack time to recognize to what extent we depend on the achievements of modern chemistry. Think this over once, looking at the bonfire. All the best.